Hello everyone, this is Saeed Domadi and I am going to present amenable sparse network investigator algorithm, which is a compression algorithm for deep neural networks. The presented results are from my accepted paper at Computing Conference 2023, which is published in lecture notes in Networks and Systems series of Springer. I am affiliated with departments of computer science and electrical engineering as well as mathematics and statistics at UMBC. The outline is the following. I briefly explain the motivation and introduce two pruning tasks. Then I will go over the optimization problem that leads to pruning and talk about the effect of initialization in pruning tasks. Then I will introduce the method and show experiments and results that we have. Basically, there are two ways of prunings. One is to take a neural network that is already trained and then make it sparse and put it on a cell phone or whatever that is useful. And the other one is to come up with a sparse trainable network. That means at the very beginning, we want to have a sparse network and we want to train that sparse network. That is the second task. Now let's look at the first pruning task, which is finding an accurate off-the-shelf network. So we have a trained network, and out of that network, we want to get a sparse network. By why solving this first task is important because we want to embed this deep neural network, or we want to use this large deep neural network to extract features, so we need a sparse network. Now let's look at the second pruning task. Is it possible to find a sparse trainable network that can be as good as the current classification networks? And in 2018, Frankel and Carbine hypothesized that the answer is yes, and they proposed lottery ticket algorithm, and they showed a way to find such a trainable network. And the focus of this presentation is about the second task. Why the second task is important? Because when we have a phenomenon and we want to model that phenomenon, we want interpretability of the parameters. So less parameters are in favor. And if we want to find new structures for neural network, we need to train them in a sparse way. Also, we want to have smaller networks on a smaller task, and we want to train them on the fly. And another one is going to be financial firms, which mandates having an interpretable deep neural network for trading, because you need to interpret that parameter for your network. There are a couple of questions that we need to answer. One is that how can we sparsify a network? And from which initialization sparse network is trainable? Can we just train it from any arbitrary initialization? This is a very important question. And can a sparse initialization be different than the original one, or the distribution is going to be different? Also, we might ask whether there is any connection between task one and task two, and if we can recover one from the other. Well, there is an optimization problem under the hood of the pruning problem. So we have the function of neural network, and we want to minimize with respect to parameters of that neural network, and we want to get least number of parameters. This problem is a bi-level optimization problem. It is a stochastic problem. Also, it is constrained because of this zero norm. It is non-convex and non-differentiable because of that zero norm. So it is a very difficult problem, and in order to solve it, we need to relax this problem. Well, for the sake of clarity, I will refer the audience to the paper for more math, but this is just approximation of the original problem by defining a mask so that we can somehow solve this very difficult problem as an approximation problem. It's good to know that the lottery ticket algorithm LTA was the first algorithm that showed we can get a sparse network by an algorithm. This algorithm just says that so we have a neural network, we will train it for T steps and R rounds. So we start with a mask that is all one, we train it toward the end. Once we have that, then we throw away weights that are less than some threshold, and that threshold is defined by 10% percentile of the parameters in each layer, and we do this for 15 rounds. But the problem is that for selecting this 10% and the R, we don't have any strategies, and that method doesn't scale to large networks and large data set. So what would be the solution? I'm going to discuss it. Actually, we saw that there are three issues with LTA. One of the issues was scalability, and LTA was not able to scale to large networks and data sets. But stabilized LTA removes the scalability problem by rewinding back the trained weights to some intermediate step as theta k, and they are able to remove that scalability by this fact. Well, why k steps of training stabilized LTA? Why it is important to start from the kth trained parameters, not from the beginning of the parameters. And this means initialization. So they just manipulated the initialization so they can scale LTA. And once we see that, the next question would be, is there any better initializations? And that would be a valid question we want to answer. Here is the method that we are proposing. First of all, this method ASNI algorithm, it compresses initialization in only 2L numbers, and L is the number of layers. It solves both tasks simultaneously. It does it in one round, and it uses sigmoid strategy, and it scales when the network gets larger. What are the key components of the ASNI algorithm? The key components are sigmoid strategy and global thresholding, which has not been done until we published the paper. Well, here is the ASNI algorithm. ASNI has two parts, ASNI 1 and ASNI 2. ASNI 1 is somehow the gradient descent, but it has a strategy for the percentile of the pruned parameters, and those percentiles following sigmoid function, and that sigmoid function depends on the number of epochs, and based on that we get a percentile, and once we have that percentile we threshold the parameters and get the new mask, and we do this using gradient descent in only one round. Once we have those sparse parameters, then we take the mean of the positive one and mean of the negative one, and these are going to be centroids where we can use them as the initialization for training a sparse network. Here, what you see is the sigmoid strategy that determines the percentile of the prune parameters. And as you can see at the beginning, it lets the network be trained with all the set of parameters, and once the network learns a little bit, it starts to prune more parameters until it gets towards the end of the epochs. Once we have this, we need to let the network to heal from the sparsification of the network, and then it should stop, and it stops at 80%. For example, for this picture, that is a picture of pruning strategy for a ResNet network. Here what you see is a three-layer fully connected network trained on MNIST. And as you can see, after doing ASNI 1, we have parameters centered around two centroids. And these centroids are important for us because we no longer have any parameters between these two peaks that you see here. And if we just take these bars, which are mean of positive ones and mean of negative ones, then we can use them as the initialization, and from those we can train a network in a sparse manner. And the number of survived parameters out of almost 266,000 is going to be almost 9,000 parameters. And as you can see, this pattern of having two peaks, positive and negative for every layer that we have, is something that you see for every layers, as well as the fact that you see we have 98% pruning at the very first layer, and 86 at the second layer, and only 50% at the last layer. That means the last layer is a layer that is important for us. Well, what you see on this slide is the power of ASNI 2. Why the power of ASNI 2? Because ASNI 1 trains the network and ends up with positive and negative parameters in blue distributions. And because of this tau OG, which is a global thresholding, we don't get any parameters in between. Once we have this, we get the positive mean and we get the negative mean for every layer, and we have these quantized version of the initialization. The question is, if we initialize the network using these two initialization, are we going to be able to train the network? The answer is yes, we can, and then we get these distributions, which are distributions of the sparse network that are trained based on what ASNI 1 gives us. Good thing is that the same thing happens for VGG13, and we get these distributions from ASNI 1, and once we have ASNI 1, we can apply ASNI 2 and train a sparse network. So the same story as we had for the previous network. Now, let's take a look at ImageNet dataset and ResNet 50, and I am just showing one stage of ResNet because it's a complicated network and we have this network. This is just only task 1 on ResNet 50 that is done using ASNI. We train it and then we sparsify the network, and this is a sparse network that can classify things for us. Well, here is the interesting thing. The red one is the learn parameters of a dense network. We have no sparsity whatsoever, and these parameters that you see are the parameters of the entire network. We pour all of them into one bag and then plot them. So this is the initialization. You can see that the initialization has the largest variance, and we see the spread that is very large. And once we have ASNI 1, we train the network, we get these blue ones that are this side and this side, and then we take the mean of each layer for positive and negative ones, and then we start training the network, and then we get these green distribution, which is like this, and we can train the network, and that's the power of ASNI 1 and ASNI 2 together. Well, this picture that you see is the ResNet network sparse at 80%, and what you see is the first layer, second layer gets sparsed less than 80%, as well as the last layer. These are the important things. The last layer is used for the classification, and the first layer is used for the feature extraction at the beginning. And you can see that all of the convolutional network in the middle um, uh, gets pruned more than 80%, and eventually we get 80% across the entire network. This is just the experiment setup. We have these data sets and these networks, optimizer and learning rate policy that is explained in the paper. We use cosine, that is a damping cosine policy with warm up, and we have parameter initialization as a k-mean normal distribution, and we use boosting training, which is automatic mix precision for accelerating the training process with PyTorch. Well, here is the page of all different data sets and networks that we use. We start with a small network that has these many parameters, and we end up with ImageNet that has more than 25 million parameters, and number of epochs, mini batch size, number of iterations, and everything is on this page. Well, this page is an important page because it shows the level of sparsity and the dense accuracy, and the accuracy of ASNI 1, accuracy of ASNI 2. And for example, for ResNet, we get 80% sparsity corresponding to 5 million parameters, and this is the dense accuracy. We get ASNI 1, so we have with 5 million we have almost 75% accuracy, and with ASNI 2, that is a trained network trained from sparse initialization, we get 75% accuracy. So we test performance of ASNI 1 and ASNI 2 against its counterparts, and these are the counterparts for ASNI 1, and these are the counterparts for ASNI 2. Well, for ASNI 1, we compare ASNI 1 with STR method, which is a method that minimizes norm 1 of the parameters in every layer, and we compare it with ASNI 1. And this method that is proposed by Google is a method that can be compared with ASNI 2 because it just fixed the sparsity at the beginning of the training, and then tries to keep the sparsity level at the beginning, and end up with the same sparsity level after the training. Here is the table that compares ASNI 1 with its counterparts, and as we can see here, ASNI 1 is able to get these number of parameters with more accuracy than other algorithms. Here is the performance of ASNI 2, which is the second task of pruning, and as we can see that starting from initialization that is found by ASNI 1, ASNI 2 can sparsify the network and get the highest accuracy among its competitors. Well, what did we learn? We learned that ASNI learns a quantized initialization, and it is able to solve both tasks, and it does it via a sigmoid strategy, and it can scale to large networks and large data sets because it uses a global thresholding. And what are the challenges that we are facing for the pruning? We have a very long way ahead because we are just uh, relaxing the original problem, and in order to get close to the solution of that original problem, we need to explore the landscape a lot to be able to get better algorithms. Here are my references. You can find these references in the paper. Thank you for watching.